Um, Hi, everyone. And I hope you all can hear me. Brian, can you hear me? No. Your microphones are muted. Deanna, can you hear me?
Yes, sir, I can.
Okay. All right. That's good. All right. So Happy New Year and welcome to week 2 of this 8-week session. And I thought it wise to spend time together just to talk about project management because it's a long chapter. And it's actually something that can be covered as a whole, almost like a whole subject on its own. So I just wanted to spend time today and ask if there's anything in the chapter that you might want me to talk about, or did you want us to go over some questions similar to what you might have in the textbook and in your homework assignments? So let's start off by just seeing what questions you all have.
This is Dina. I did have a question about crashing the project.
Okay.
I was a little confused on that, how you can really figure out what works and what doesn't work.
Okay. Okay, that's good. That's fine. Anybody else have something you'd like us to review?
Hi, Professor. I just had a question on the Gantt charts.
Okay.
Whenever we stack some of them, whenever they have the same preceding requirements, like how do you know if like one's shorter, like where it goes on that? And like, does that make sense?
For the Gantt charts, okay, I'll talk about that. Okay. And I would usually tie the Gantt charts into your network diagram. When you're drawing that, it can tell you what precedes what in the diagram. Okay.
Right.
But let's talk about that as well. Okay, any other questions before I go into a discussion? So project management is obviously a topic that's of interest to everybody, regardless of what area of work you find yourself in. If you're in finance, if you're in marketing, operations, accounting, there's always a possibility that you could benefit from the use of project management tools. So this is one of those chapters in the textbook which is very practical and applicable to almost every branch of business that you'll be in. I'm going to share my screen here. And let's move from, I'll come to crashing last because it's the last part of our chapter. Let's go to, Okay, so as you go through the chapter, you'll notice that there are two basic types of approaches to project management. You can either use the CPT approach, the critical path method, or you could use the CPM or the PERT approach. Okay, the difference between the two approaches is that the critical path approach assumes that all the data, all the information that you have is given. Okay, if activity A takes 10 weeks, we believe it's going to get finished in 10 weeks. So there's no probability associated with that. Okay, and that makes it easier to be able to work through a critical path problem. Okay, the PRT approach to project management is slightly more in line with expectations. If you look at the fact that for most projects, you start off with a given time duration for different activities, but there's always a chance that something might go wrong. COVID might hit, something might happen that might extend the duration of a given activity. Okay, so the difference then becomes that PERT has probability incorporated into the calculations that you'd have for any given problem that you're faced with, right? So let's, before I go into the Gantt chart, I just wanted to ask, did you guys have, for those who've looked at the homework assignments, were there any problems with the CPT diagram, CPM diagrams, and PRT diagrams? and calculating earliest start, latest starts, earliest finish, latest finish. Did you guys find that okay?
Yeah, I did.
Yeah, I found it fairly straightforward.
Okay, that's good. So even the backward pass was okay. In terms of how to go about figuring out, if I'm given a project like this one here, how to put together the diagram, it should be very straightforward if you understand the simple addition and subtraction associated with calculating the earliest start, earliest finish. But from this, I can come up with a network diagram and then put together a Gantt chart, which would then enable me to see how do the different activities flow into each other. Okay, so let's start off with the network diagram, and then and I want one which has the, okay, this one here has your critical flow. Okay, now if I'm translating this project here into a Gantt chart, I'm obviously going to start with the very first activity, whatever that activity A is, okay, and start it off at time period 0. Okay, let me bring out a pencil here. And I don't have the, should have used my MacBook. Okay, so now let's look at this and let's compare these two here. Okay, activity A here starts as time period 0. Okay, we're now creating my Gantt chart. I want to make sure that those start activities will start from time period 0, and everything else will flow from the information that we have on our network flow diagram. Okay, so we start at 0. The time duration for activity A is 2 weeks. So I expect that activity to take 2 weeks. Okay, now with regards to how do I know when something should flow into out of, say, activity A or B, I would go back here and see when does a specific activity end, because the next activity that flows from that activity cannot be started until you've finished a given activity. So C cannot start until I've finished A. So in my Gantt chart, I'm going to ensure that C only starts upon completion of A. Okay, and that's how you keep it moving. You look to see after we're done with C, we have F and E. Okay, so both these can only begin once activity C is complete. Okay, and they'll start right after that activity is complete. So if I look to see, C here ends, is that week 5? And you'll see E and F will start right after that. Okay, the length of the bar here in a Gantt chart represents the duration of time that that specific activity is going to take. So when you're putting your Gantt chart together, you want to be able to have at least visualized what the flow is from each and every activity into the next. Okay, now we actually have it's not required for this class, but we have Gantt chart mapping softwares, which makes this, if you're using project management tools, will make this much easier to do. Especially if you're in corporate and you work in project management, your company should be able to source those a software that's specific to what the company needs would be. Okay, but putting the Gantt charts together is very much a part of being able to put together the network flow diagram first. Okay. When it comes to the Gantt charts too, there are 2 types of Gantt charts. You're either going to determine that you want to use an earliest start, earliest finish Gantt chart, which gives you the earliest dates that you can start or finish a project, or you might be interested in figuring out how much time do we have if we have to start different activities as late as possible. How much total time do we have that's going to enable us to finish the whole entire project within that 15 or 16 weeks that we started off with. Okay, so the difference between the earliest start, earliest finish Gantt charts here and the latest start, latest finish is that now we're looking at what activities can we actually push out and start at a later time without stopping, without increasing the whole project by any extra time. Okay, so you'll notice here that, let me bring out my pencil. Our end time here for the latest finish will be the same as the end time for the earliest start, earliest finish. That stays the same. The other thing that stays the same will be when we start the project itself. So these times here stay the same for both. The only thing that can change is what's in between the earliest, the very first activities and the very last activities. Okay. Trying to think of if that answers your question. And was that Andrew asked this question?
Yeah, it does. The only thing I was having trouble with was on the homework. I was confused on whether you wanted to, like, for example, like looking at E and F, they start at the same, like they have the same like preceding requirement.
Right.
But I was just confused if like for example, F, was it supposed to end at 9 or like start with the same one at 5? That's the only thing I was confused about.
Yes, so that's a really good question. So they both start at the same time, right? But the amount of time that it takes to finish activity F is slightly shorter than the amount of time it takes to finish E, right? So F takes, I believe here, 3 weeks. E takes 4 weeks. And that tells me that if there's any activity that has to start after these two activities, we'd have to wait for the longer of the two activities to end before we can start the next activity, which I believe is activity G. Okay, so it kind of leaves, F has some wiggle room there, which we call slack. And that slack is critical to the project manager, because anytime we have an activity that has slack, it's an activity that we can decide to pull resources from and go and work on other activities. Okay, and maybe that way we are using our resources more efficiently rather than just letting our resources stay idle until the next activity is ready to be done. But that should be how you'd view this. If there are two activities that have the same start, but I mean the same start time, but not the same duration, if there's any subsequent activity after that, we have to wait for the longer of the two activities to be completed before we move on to the next activity. And that's why activity G can only start after F if it was along the same path. Let's see, G. Okay, so in this case here, G is not on the same path. G follows E and D. So that means that when I'm looking at this Gantt chart, I'm looking to make sure that D and E are complete before we finish, before we embark on G. Okay, because E takes, it gets finished at a later time period, I'll have to wait until E is complete before I start working on G. Okay. So this again is, I believe that was C, the critical path method, because I didn't see any probability associated with the Milwaukee paper. Okay. For instances where we actually have, where we believe that we should incorporate some variability because we are not sure about the future, the PRT or part approach works much better. And we end up having a situation where we have to calculate how much time exactly do we need, or do we expect the project to, a given activity to take, okay? And we assign that the letter M, or the most likely time that it will take. But we also have two other times that we're going to discuss. We're going to have to possibly figure out what's the least amount of time that we can take for a given activity, or what we call the most optimistic time, which will be less than M. And then we'd also have to look at a worst case scenario or a pessimistic situation where our given activity takes longer than we initially budgeted it to be, okay? So usually under PERT, M would be say 10 weeks, A, which is your most optimistic time, would be if we have all our resources lined up well, we could possibly finish this activity in 8 weeks. B, which is our most pessimistic time, would be a situation where we expect the project to take, that activity to take slightly longer. And so we use that, okay? So under part, we're required to have those 3 times, and we're going to then combine them into some aggregation that's going to enable us to come up with the most optimal or expected time that we're going to have for each and every activity. Okay. So for part, the one question that I usually find a lot of students find confusing is when they're asked about variance and how to calculate variance. Let me clear these drawings. Okay, so these 2 formulas are basically what constitute the calculations you need to remember if you're ever doing a project using the part approach. Okay, you want to know what your expected activity time will be for each and every project. Okay, and that's your A plus form M plus B divided by 6. And then in addition to that, given the values you used for your A, your M, and your B, you also want to calculate how much variance should we expect for a given activity, right? And let me give an example here of why this is important. Pencil. So say we have A equal to 9, M equal to 10, and B equal to 11, okay? And I want to first of all calculate my expected activity time, and that would be 9 plus 4 multiplied by 11. Sorry, multiplied by 10 plus 11, and I'm going to divide all that by 6. Okay, and what do we get here? That's 40 plus 20, that's 60. So we come up with an expected activity time of 10 days or 10 weeks, if that was the case. Okay, let's go with weeks. Okay. Now, that value in and of itself does not fully give me the amount of risk associated with that activity. And that's why I want to also calculate my variance associated with those times that I have here. Okay, variance just tells you how much fluctuation do we have around this 10 weeks. Okay, the bigger the figure of variance is, the more risky it is that we might not be able to finish a given activity in the time that we actually have it. Okay, so I want that figure of variance to be as small as possible for each activity for me to gain a measure of assurance that we should be able to finish it within that 10 weeks. Okay, so using this information here, I can calculate my variance as 11 minus 9 divided by 6, and I'm going to square all that. So that 11 minus 9 would be 2 divided by 6 squared. Okay, and I'm going to do this in Excel because I don't know what that's going to look like. Equal to the square, no, equal to 2 divided by 6, and that raised to the second power. Okay, so now my variance value for this information I have here is 0.11. Okay, and that's a very small figure. So that tells me that the smaller your variance is, the more likely that you should be able to finish a given activity within that time period that you already set up in your expected activity time. Okay, now this would differ from a situation where, let's use these numbers here. Let's use 1, 10, and maybe let's use what? That's 9, 19. Okay, So if my A or most optimistic time is just 1 week, most pessimistic time is 19, and my most likely time is 10, my expected activity time would then be 1 plus 10 multiplied by 4 plus 19, and I'll divide all that by 6. And what does that give me? 40. I'll have the exact same amount of time as in the first calculation. So my expected activity time here will be 10 weeks. But now the difference arises in the variance. Okay, whereas here the variance is pretty low, 0.11. In this second scenario here, my variance will be 19 minus 1 divided by 6, and I'll square everything. So that'll be 18 divided by 6, which is 3. And now my variance, what's that, 18? Yeah, 3. My variance now will be 9 weeks. Okay, so I move from a variance which is less than a week, less than a day maybe, to a variance of 9 weeks. So there's a lot more riskiness with a situation where my activity times, the expected times are all over the place. Okay, so we want to try and control the amount of variance to give us a better estimation of how much time exactly a project is going to take. Okay, and once you've calculated your expected time, your variance, a question that arises is, what's the total variance of a given project? Okay, so if you have 10 activities in a project, you calculate the variance for each and every activity, but the variance for the project as a whole is not going to be the sum total of those variances. You're just going to add up the variances associated with the activities on your critical path. Okay. So, and I guess you must have gone through this if you're doing the homework. So we set up the same activities A through H. We calculate our optimistic, most likely pessimistic times, and then calculate our expected times for each and every activity. Calculate our variance for every activity. But if we don't know the activities that are on the critical path, it becomes hard to know what's the total variance for this project. Okay, so let me move this out of PowerPoint and into Excel. Oops. You do that to me. Okay, so once we've come up with all our different activities here, one thing you want to calculate is your what are the activities on your critical path? Okay, the activities on the critical path are the activities that will lead us to determine how long this project is expected to take, right? And this is where that network diagram comes into play. If you have the network diagram, it becomes very easy to visualize how each and every one of these activities fit into each other. If you don't have the network diagram, you'd have to do the earliest start, earliest finish activity approach. And that way you'll be able to figure out exactly when each activity starts, when each activity ends. Okay, and that's always going to be based off of your expected times. Okay. And if you have a question, please feel free to jump in. Okay, so you'd calculate your earliest start, earliest finish, latest start, latest finish. And always start with the activities that on your diagram show start as a very first start activity. Okay. Okay, so keep in mind we're interested in the project variance being the variance of all the critical path activities, meaning that when you're looking at the activities along the critical path, those are the variances that you're going to add up together. So here we had what, A, C, E, G, H. A, C, G, and H. What are those four? A, C, G, A, C, E, G, H. Okay. So I'm interested in the variances for these 5 activities. That's all I'm going to do is add up those 5 variances, and I come up with the total variance for the project. Okay. So the combined total of just those 5 activities tells us how much variation we can expect to have for this project. So that plus that plus that. Around total variation will be approximately 3.11 weeks. Okay. Now, any questions on part before I go into project crashing? You guys are project management gurus who understand how to do simple probability variance calculations. But one question that you might have as a project manager, or if you have to lead a project, would be to answer the question of what if my project duration, according to the math here, shows 20 weeks, and I want to know what's the probability that I'll finish this project in 16 weeks, okay? That's always something that you want to be able to figure out. Is there a probability that this project can actually be completed in a shorter period of time? And also it could be that I want to know the probability that the project will take longer than the 20 weeks that we've estimated, okay? And if ever you have to figure that out, you have to have, let me go there. Okay, you have to know what's your expected date of completion, okay? In this case here, that'll be looking at the sum total of, get rid of all this color. I'll only be looking at those activities on the critical path, G and H, okay? So this critical path activities tells me how long will this project take at a maximum, okay? So my project's expected to take around 15 weeks. And if that's the case, the question that would arise is what's the probability that we can finish this project in 13 weeks, for example? Okay, or what's the probability that we will finish this project in 16 weeks, given that we estimated it would take 15 weeks? Okay, those are valid questions that a project manager might want to ask and test, because there's always a possibility the project might go a week extra or a week longer than expected. And what that means for me as a project manager is that I might have to be spending an additional 1 week worth of resources, be it employee time, computers, things like that. And so I might want to factor that into my whole project budget. Okay, so to be able to calculate that, we need to know these two numbers, our expected time calculated, and we also need to know what's that time that you're trying to estimate that the project might take. Okay, so it could be 18, it could be whatever number the project manager looks at. Okay, so we're going to use a combination of these two values here, as well as your figure of variance. And this is where the variance comes into play. Okay, because the variance is the one which tells you the level of risk associated with accomplishing a project within a given time period. Okay, so going back here, we've calculated that our expected project duration is going to be 15 weeks. Okay, we have another value here that we don't have on here. Okay, here we have a variance figure of 3.11. And I'm going to get the square root of this value. Square root of SQRT. And I have, let's make that bigger. I get this value here, 1.76, okay? Now, the 3.11 is our project variance. This here is our project standard deviation. Okay, so we use this project standard deviation in conjunction with expected time, and this projected time that we want to try and estimate whether or not what's the probability associated with finishing the project in say 18 weeks. Okay, and we calculate a z-score linked to these values here. And the z-score is usually calculated using something that looks like this. Mu divided by x bar divided by the standard deviation. Okay, and if you have those values here, this will be our target value of 18. This x bar here will be our average expected time, and this would be our standard deviation. Okay, so in doing the math here, 18 minus 15 divided by 1.75 gives us a value, or z value. Okay, and once you calculate that z value, you're going to take that z value, go into a z table, which is given at the back of the textbook, and calculate what's the z-score associated, what's the value associated with that z-score. Okay, and that value associated with the z-score then tells you the probability that you're going to finish this project in a given amount of time. Okay, so let's do the math on this here. I'm just going to do it here. So we have here 18 minus 15 divided by 1.76. Okay, and I get this value here called, the value of 1.70. Okay, so this is my z-score, and we want to convert the z-score into a probability. Okay, you can use the z-table, or you can just use an Excel function and very quickly figure out what the probability would be. Okay, so I'm going to use a formula. Should I use norm dist or norms in? Let's try norms dist. Okay, so if you use the norm dist, let me make this bigger. Norms dist. And it'll ask you what's the z-score that you calculated. So I'll just click on that, and it gives me a value. Okay, and the value that I get here is that I have a 95% probability that I'll finish this project in 18 weeks. Okay, a 96% probability that we'll finish this project. There's always, you never ever get to 100% probability. So this is pretty accurate, and say, yeah, if the project was expected to take 15 weeks, then there's a very, very high probability that you'll finish it within the 18 weeks that you anticipate. Okay. You could alternatively ask, what if I wanted to see what's the probability that I'll finish this project in 13 weeks, which is less than expected time. Okay. If that's the case, oops. We get a different probability here. Okay. And the probability here tells me that on the basis of our calculation of expected time, there's a 13% probability that we're going to finish this project in 13 weeks. Okay, so much lower than the prospects of finishing this in 18 weeks. Okay, so again, that formula used here is called the norms dist formula. It pretty much does what you do by going into the back of your textbook and looking up the z-score. I find this much more convenient than pulling out my textbook, which right now is at the office and I'm at home. Okay, so some of these Excel functions are very convenient, very easy to use, and let you arrive at an answer much faster than going through the back of the textbook. Okay, so these are just some of the things you can do as a project manager trying to figure out whether or not your project will be complete within a given amount of time. But sometimes a problem might arise, and let me just take this out. I'm trying to, let me go back and ask, who was that who asked this question about project crashing? Was it Dina? Dina, you asked about project crashing? And
I did, yes.
Yeah. So project crashing is important to the project manager because sometimes any extra time period, any extra week, any extra month that a project is delayed usually translates to a cost to the company, right? And if you work in corporate, I quit corporate around 7 years ago. Time is always money, right? So sometimes you have this cost where you have to run a quick cost benefit analysis. Should I try and pump in additional monies, additional resources to a project to try and reduce the amount of time it might take and possibly save the company some money? Okay, so that's where project crashing comes in. Okay, because whenever you're trying to crash a project, it comes at a cost. The question is whether or not that cost is what the benefit of reducing the amount of time that the project would have taken initially. Okay, so that's the overall thought process behind trying to see whether or not we should crash certain activities associated with project crashing. Okay, now for any project crashing question that you'll get, there are a couple of costs that there are 2 types of costs that you will be looking at, and there are 2 types of times that you'll be looking at. Okay, the first cost is the normal cost of doing an activity within the time frame that you initially set up to finish an activity. Okay, so if activity A was supposed to take 2 weeks, the cost associated with those employees and the equipment and the resources could be, say, $1,000. Bring out my pencil. Okay, so usually you start off by calculating a normal cost, because this is what you start off with once you've done your budgeting for your project. And then the question arises of, okay, if we were to try and do the same activity in a shorter period of time, we might have to bring in Kevin. Okay, bringing in that extra resource is going to cost us some money. Okay, so your crash cost is almost always going to be higher than your normal cost. Okay, so this is where you're going to have a cost that is, say, $1,500. Okay, now because we are adding a resource or an extra person or adding extra equipment, our crash time here should always be less than the normal time, because the overall objective is to try and reduce the total amount of time it'll take for us to complete an activity. Okay, so again, in your denominator here, when you're first planning your project, you're going to figure out your normal time. That's the time that you have in all those tables. Once you've done your activity mapping and figured out how long each activity is going to take, you have your normal time. Okay, the crash time is the time associated with adding Kevin to the project. Okay, so we expect that if the normal time here was 5 minutes, well, 5 weeks, our crash time could possibly be, say, 4 weeks. Okay, and this calculation here leads to what we call the crash cost per period. How much is this benefit of what's the cost associated with reducing the amount of time by adding an additional resource? Okay, so here we have 1,500 minus 1,000. In the denominator, we have 5 minus 1, so that gives us what, 500. divided by 1. And I'm going to say that my crash cost per period for this period here is going to be $500. Okay. All right, so let me clear that. So just keep that in mind, and let's look at a problem here. Oops. Let's take this and put it in Excel. Oh, no. I was hoping it was something I could just copy and paste into Excel. All right, we'll recreate it over here. And bear with me. Activity, crash. So we have A, B, and there we have 2. It's 2, 3, 2, 4, 4. 5, 4, 4. 1, 1. 3, 2, 2. Then we have 22, 750, 34. 500, 500. Okay, we have time there, and we have cost here. Okay, so we start off with this table here where we have all the different times, the normal times, the crash time, the cost, the normal cost, the crash cost, and we want to use that formula to try and figure out what exactly is the crash cost per week going to be for each and every activity. Okay, and this is why it's important for us to understand that there's a reason why we need to figure out what are the crash costs for each and every activity, because we're going to use that information to figure out what activity should we crash first. Okay, we're not going to crash all activities. We just want to crash activities until we get to that amount of weeks that we need to get to. Okay, so our crash costs per week become our next concern. Per week or per time period. And now we use that formula we have for a crash cost per week, which was your crash cost minus your normal cost. Divide that by your normal time, kind of backwards, minus your crash time. Do I have a problem with my formula? Yep. Okay, and I'll drag that formula down. These are all costs. Okay. So now I'm going to use this column here to answer the question of what activity should I crash first? Okay. And let me ask the class, what activity do you guys think we should crash first?
Go with the cheapest.
Okay, sounds good. Anybody else have a different opinion? So what you said is correct. We start with the cheapest activity, but there's a caveat there.
Yeah.
It has to be the cheapest activity on the critical path. Okay, because you don't want to crash an activity that's not on the critical path, because it's really not going to save you any time. Everything on the critical path, if I reduce stuff on the critical path by 1 week, my whole project reduces by a week. In this case here, we have F, which seems to be the cheapest, but F was not on the critical path. So even if I reduce F by 1 week, it doesn't really, if the whole project takes 15 weeks, reducing F by 1 week won't change the duration of the project. But if I, on the other hand, let's get rid of this. I'd look to see what are the activities on the critical path. I believe we had A, we had C, we had E, and then G and H. Okay. Now I can go back and ask myself, of these activities here, what has the lowest crash cost per week? Okay.
A.
Now that takes me to A. Is it A? Yeah.
Yep.
Okay. So A has the lowest crash cost. So let's crash activity A first. And so we reduce the amount of time for the whole project from 15 weeks. You can only crash it by 1 week. Okay, what this means here is that we can only crash activity A by 1 week. So we move from 2 weeks total to 1 week. And that means that we move from a total of 15 weeks, and that brings us down to 14 weeks. Okay, if our target was 13 weeks, then I have to go back and try and figure out, this is done. I cannot crash A any further. Okay, so I have to look for another activity to crash. Okay, and once you've crashed an activity, something tricky happens. When you reduce the amount of time duration on these activities, it could be possible that the critical path stays the same. And if that's the case, I would look to see what's the next activity to crash. I could possibly crash this one here or this one here. But chances are that when you reduce an activity by a week or two, some other activity might now become part of the critical path. Okay, so that's when it becomes a bit tricky, because now I have to go back to my network diagram. Let me try and get that.
Yeah, I noticed that on the homework.
Oh, yeah.
Yeah.
Yeah, it becomes very tricky. So right now we are saying we're crashing A, activity A. This is what we're reducing. So we're reducing this time from 2 to 1. Okay. And once I do that, I'm going to have to recalculate each and every path here. So there's A, C, F, H, A, C, E, G, H. There's B, D, G, H. So my first iteration here reduced, we started off with 15 weeks. With this new change, we're down to 14 weeks. So I'll have to ask myself, is there any other path here which is at least 14 weeks? Okay, so I'll look at A to C to F to H. That'll be 1 plus 2, that's 3, 6. So that is what? 6 plus 2, that path gives me 8. I want a path which is at least 14. So this doesn't make a difference. That doesn't become a critical path. Next, I'm going to look at B to D to G to H. And that is 3 plus 4, which is 7, plus 5, is 12, 13, 14. So notice now that we have another path which is also got 14 weeks. Okay. So our original critical path is now, we now have 2 critical paths. By reducing A by 1 week, we end up with 2 additional critical paths. Okay. Now, how does that translate onto our spreadsheet? It means that all these activities here, B, D, G, and H, are added to our. So I'm going to now add B, and D. Let me use a different color just to, let's use, I'm not good with colors. No, I need it to contrast. So B and D get added to the mix. Let's get rid of the pencil. Okay, now I consider everything that's shaded here and look and see what's the next lowest cost we have. Okay, and here I see we have 3 activities which have 1,000, the crash cost is 1,000 a week each. So any one of those 3 are activities that I could decide to crash. Okay, now whenever you're crashing, you only crash one time period at a time. What I mean by that is E here has 2 weeks that could be crashed, D has 3 weeks that could be crashed. But I will always just crash 1 week at a time, go back to see how does that crash affect my network diagram. Does it add F to the mix? Because if it does, then I might be able to crash F because that's the lowest cost we have here. Okay, and it's kind of like it's a repetitive process. If you're using project management tools, it can do it for you. If you're using Excel, it'll be up to you to try and visualize it while you're crashing each project one at a time. I mean, sorry, each activity, not each project. Each activity 1 week at a time. Okay, so if we decide that we are crashing, let's go back here. There's nothing they share in common apart from the last 2, which are pricey, so I can crash any other. Let's crash activity C. Actually, let's start with activity D. Let's reduce this by 1 week. Okay, so when I do that, we're going to incur a cost of $1,000. So now this is a cost that we're going to be incurring $750, an additional 1,000. Okay, but that now reduces our activity time here by 1 week. So we're down to 4. And when we do that, our critical path reverts back to the original critical path. Okay, because now we're going to be having 14 weeks on the original path and 13 weeks on our second path. Okay, so for the third iteration, I'm going to go back to that critical path of A, C, E, G, H, and crash one of the other activities, which is at the lowest crash cost. Okay, and you do that until you get to the amount of weeks that's required in the question. Okay, and let me look at the question we had here and try and see how many weeks were they expected to crash. I guess it's not completed here on the PowerPoints. Okay, but does that make sense, you guys? What do you? Is anybody got a question on crashing? Okay.
I think.
Yeah, it's just a matter of understanding that crash cost per week, not cash, crash cost per week formula. Once you've calculated that, look for the lowest cost per week, start with that activity as long as it's on the critical path. Okay, and that's why we did not use F, because F was nowhere along the critical path. Okay, so that's completely ignored until it becomes critical. Okay. All right, I guess we'll give it a shot on the homework assignment, but any questions, I think, before we wind up? On anything, the syllabus or any other thing? Silence means we're good. All right.
I guess one question I have on the case study, on the part where it says to make the diagram, what would be the best tools to be able to make the diagram part for the first part of the actual case study?
For most of what I use, I use Excel. Let me make a small video tutorial that could help you on that. And I'll post to Blackboard. Let me try and make it tonight and post it to Blackboard. It should be like a short 10-15 minute video.
Okay, that'd be great. I'm going to try and knock it out tomorrow.
Okay, sounds good.
All right, thanks.
All right, thanks. All right, so let's call it a day, and I'll be on here again next week. As I mentioned, the Zoom sessions are optional. And usually for those weeks when you have calculations, they could be helpful, especially if you run across some homework problem that you really needed some additional support on. Okay. All right, you all have a good rest of your day, good evening, and I'll hopefully speak to you next week.
Thank you.
Okay.
Thank you.
Thank you.
Okay.
Thank you.